So last time I gave an extremely brief introduction to what Reach is about, and I kind of walked through what the tutorial was about, but we didn't actually go through any of the components of it. And I think that today what we'll do is we'll kind of take that slowly and go through these things. Um, so to get some context, just so that my brain is on the right track, when you use Reach, you're basically using a special Docker container that we've prepared. So to use it, all you need to do is make sure that you have some really basic Unix tools installed, like make and Docker Compose. And all of these things work on Windows, especially when you use the Windows subsystem for Linux, the WSL feature, which is really awesome. And that's what I'm using. So if you're watching this and you're like, oh, I'm on Windows, how do I do it? Well, you're watching someone do it on Windows. And before I used Windows, I used OS 10. So, and it works really nice on OS 10. And obviously it works nice on Linux too, because it's kind of everything else is just emulating Linux. So anyways, when you write a Reach program, you are really going to be writing two programs. One program is the Reach program itself, which describes your DApp. Now, what is your DApp? Remember, your DApp is what Reach's perspective on what a DApp is it is a decentralized computation that a number of participants are going to be collaboratively performing. And they want to run this computation without trusting each other. And what it means to not trust each other is that at various points in the program, they're going to make assumptions about how other people computed something, and they can't trust that. So they can't just go from that assumption to making important decisions. And when I say important decisions, think spending money. That's an important decision. So you can't go from having this assumption to making an important decision without actually checking it first. And the role of the consensus network is to perform those checks in a way that everybody can know were done properly. So that's a perspective that Reach has. So that now what that means is that what your DApp is all of these different participants interacting, and then the consensus network that intermediates between them. So when you want to really test one of these things, that means that you have to create, each one of the participants, and then you also have to create the consensus network and hook them up all together. And so that's kind of a complicated process. So Reach abstracts all of that by using these Docker containers that I mentioned before. And one of the perspectives that the tutorial takes is that you often want to build a test scenario for your program, and we write that test scenario in JavaScript. And so you'll write your Reach program, but then you'll also write a test scenario. And the test scenario, I'm going to open up another file in JavaScript. And actually, let me make my screen size bigger. How do you feel about the screen size? You want it larger than this? I'm going to copy and paste this blob in, and then kind of talk through what each one is. Okay, so when you write your test scenario, you're going to be requiring the Reach standard library, which is a helpful library for helping you write these front ends, which is what we call each one of the participants. And it's called the front end because in a real deployment, it's like a user interface that interacts with a real human being who decides, for instance, like, what hand of rock, paper, scissors you want to play or what trade you want to make. So anyway, so we require this library. We also require the compiled form of your Reach program. So when you write your Reach program over here on the left and compile it, you don't like run Reach programs. What they do is it creates the code that would run each one of those participants and the consensus network. And so that is admitted as a giant JavaScript program that has pieces of it for each one of those components. Now, we use promises extremely heavily inside of our Reach programs, inside of our JavaScript code. And we highly recommend using the async await pattern. Now, I feel like I should explain what promises and async await are, even though that is not really a reach thing. But I feel like maybe there are some, new enough developers that it would be worth explaining this. If anyone thinks that this is a terrible idea for me to explain this, please say something right now. Okay, so kind of a fundamental thing that goes on in programs is you do something and then you wait for that thing to be finished. And waiting for something to be finished is called blocking. And JavaScript was designed to not allow any blocking. And why was it designed like this? It was designed like this because JavaScript is seen by many people as existing purely to run little programs inside of your browser. And there was this goal to make it so that those programs, if people made a mistake writing them, they couldn't make the browser completely lock up. And so they actually made it so that there was no way inside of JavaScript to block. And that's actually a very forward-looking idea because in other programming languages like C or Java or even fancy languages like Haskell or Racket, all of those languages have this default assumption that the things that you're going to do are going to block. And then they make it a complicated programming pattern to not block. But in JavaScript, not blocking is the default. But the problem with not blocking is that, well, like you have to block because you're going to do something and then you want to wait for it to complete. And so what has emerged in the JavaScript world is what's called a promise. And what a promise is a representation of a value that will be available in the future. It is basically the thing that you are blocking for. So an example of this would be like you send a network request to download your email, and then what gets returned is not your email, but a promise that in the future you will have your email. And so then what you can do is you can treat that promise as though it were the actual value. And modern JavaScript allows you to take those promises and operate on them as if they were actual data. And this will, of course, return a larger promise. So think of it like this. You get a promise for your email, and what you do is you run the operation, I don't know, search through your email for the word J, and then it's going to return a list of all the times when it appears. So you started with a promise for your email, and now you have a promise for a list. And then you'll take that list and you'll look at the length of it. Now you have a promise for a number. And then you'll take that promise for a number and you'll send it out to be printed. And so this is called a promise chain. And these things are produced automatically by using asynchronous functions. And what await means is when you call await, this function returns a promise, and I'm going to treat that promise as if it were the actual value, and I'm going to call that actual value standard lib, for instance. And so every time you see these async, and await functions, basically what that means is that async signals to the JavaScript compiler, I want you to do that promise chaining thing. And when you write await, what that means is this function on the right here returns a promise. Let me treat it as a normal value. Now, if we were to convert this to like Python or something like this, the code would look exactly the same, except that we would just delete all the awaits, because in Python, you can write blocking programs. So all of these steps that can't block in JavaScript, they would just block in another language. So it kind of feels like, I don't know, the annotations that you have to write on your code sometimes in programming languages that require you to annotate types. It's basically like you're leaving hints for the compiler to make its job easier. Okay, well, that was kind of like background material, not really related to reach, but hopefully that's interesting. So what we do in this little program is we first load the standard library, because reach supports many different blockchains, and the standard library is customized for each one. There's a chat message. So there's a custom one for each chain that we support. And so what this load standard library function does is it looks in your environment for some indication about which blockchain you want to connect to, and it will load the appropriate standard library. Then what we do is so every blockchain has its own notion of what's called an atomic currency. So for instance, in Ethereum, there's this value called a Wei. And a Wei is a 10 to the negative 18 ETH. And so when you do operations inside of Ethereum, you're actually operating on these Wei. You're not operating on ETH. And similarly on Algorand, there are micro algos, and pretty much every blockchain has one of these concepts. But there's a notion of what people mean when they, like, what is the user-facing currency? And so this parse currency function, what it does is it just converts a user currency to the core thing. So this 10 would be multiplied by 10 to the 18 on ETH, and would be multiplied by 10 to the 6 on Algorand. Then what we do is we create two test accounts. So this function that we're calling right here is called standard lib new test account. And so one of the things that Reach can do is that when you run this test program, we can test on a completely private, newly created development network. And that development network has all of the monies completely unlocked, so that we can just create an account and give it 10 ETH. Now, of course, like 10 ETH is like, $30,000 or something like that right now. But in your network, it'll be worth 0 because your network isn't the real Ethereum network or the real Algorand network. And so what this does, it will create one of those test accounts and we'll name it account Alice. You don't have to name them this ACC. That's just what I like to do to help remind myself what the type of this variable is. Account Alice. We do the same for account Bob. Now, those two accounts, they now have the ability to manipulate their funds. And because they can manipulate their funds, they can use those funds to take actions on the chain. And pretty much one of the assumptions of consensus networks is that because everyone in the world is replicating your computation to verify that it was done correctly, you have to pay them for the privilege of doing that. And so that means that every time you do something, you have to pay, thus you have to have an account. So one of the things that every Reach program is going to do is that somebody is going to deploy the program. And so we write account Alice.deploy. And so she is going to deploy it. And now what does she deploy? Well, she has to deploy the compiled contract. And that's why one of her arguments is the backend. Recall that the backend is the file that was generated when we compiled the Reach program. Let me just do that real fast so you can see what I'm talking about. So I'll write Reach, compile, and it's going to compile index.rsh. And then it creates this file right here. Look, see in the build directory, it says index.made. It was made on May 20th at 10:27, which is basically what time it is right now. So that file was just made right just now. And if we were to look at that file, it's got lots of cool stuff in it. So all that is, the code that got compiled. Right. Okay, so that's the thing that we're actually deploying. Now, once we deploy that, we now have a representation of the deployed contract, which we call contract Alice. And inside of that representation is going to have details about exactly what was deployed. So for example, on Algorand, what it means to deploy a contract is to allocate what's called an application ID. So that application ID is going to be inside here. In contrast, on Ethereum, what it means to deploy a contract is to create an object, and that object has an address. And so that address would be inside of this object. We call that the info. So we write right here, see contract alice.getInfo. Because the contract will only be deployed a single time, and then every other participant in the program, they do what's called attaching to it. Now notice that when they attach, that requires them to have an account, because what they're going to be doing once they attach is they're going to be potentially sending messages to it. And so notice that we have to give it the account information. We have to give it the contract information so it knows what it's attaching to. And notice that we also give it the backend. And this is actually kind of an important deal. Like, why are we giving it? Like, it doesn't need it because it's not the one doing the deployment. Well, one of the things that you should always do when you write a blockchain program is before you start interacting with the program out there on the internet, on the consensus network, you have to make sure that you know what the code is. Because if you start transferring it funds, you want to make sure that it is going to treat those funds the way that you think it should. And let's actually step back one moment from the technical details to the bigger picture. Remember, what dApps are a whole bunch of participants doing a consensual computation where the consensus network guarantees that they are all following the same rules. So what that backend object represents is what those rules are, what the program is. And so we want to make sure that the consensus network program, the contract, is actually implementing the rules that we think it should be implementing and not some other rules. And so that's why we have to give this information. And so behind the scenes, what happens is something that's called contract verification, where we download the source code, we download the compiled code that's on the consensus network, and we compare it with what we think it's supposed to be. Okay, all that was just, a whole bunch of boilerplate, but it's interesting. And now what we're going to do is we're going to actually run our test scenario. And our test scenario is going to start a representation of the participant for Alice and another one for Bob. Now this kind of goes back to one of these JavaScript things. So in JavaScript, remember, there's no blocking, but there's also no threads. And remember, what threading means is it refers to multi-threading, where you have one program that's doing multiple things. The idea is that your program is like, like a string of fabric, and a string of fabric is made up of many individual threads that are all wound together. And the job of the fabric is only done by all of the threads working together. And that's where that's how your close work. There's not one thing. So anyways, so we want to have our test program have a part of it being Alice and a part of it being Bob. And the way that we can do that is we can call this function right here, backend.alice. And this, notice it's part of backend, so that means it was generated from the reach program. What it basically is we take the reach program and we slice the reach program. We slice the part of it that is related to Alice. So you can think of your reach program as being made up of the entire computation. And there are some parts that Alice does, and there are some parts that Bob does, and they're all mixed together in the reach program. And what the reach compiler does is it separates them out. And when it separates them out, it sort of like matches them. So in one part of the program, maybe Alice sends something. So that means that Bob is going to receive something. And then Bob sends something. So that means that Alice receives something. So in the reach program, you actually are only going to specify one of those operations. Basically, you're always going to specify who sends what. So you're going to say Alice sends this, then Bob sends this, then Alice sends that. And so because you are only specifying one side, what a reach does as it's compiling is it figures out, well, what the other side would have been. And it does this for not just two participants, but actually does it for any number of participants. So this is a process that we call endpoint projection. I say we, but obviously I mean me. I call it endpoint projection. It's this analysis that I came up with as part of my PhD dissertation like 15 years ago. But it's just this example of this larger technique that's called program slicing, which comes from verification. Okay, so these backends, they need to know what contract they're working with, what contract they're attaching to, and then they also have to have some more stuff, which I'll tell you about later. Now, each one of those backend functions is going to return one of these promises. And so there's this function that you can call in JavaScript. It's called promise.all. And what it does is it takes an array. See how there are these brackets here? That means that this is an array. It takes an array of promises and turns it into one promise that is for the array of all the contents. And so basically what it does is it sort of changes the types. So if you think of it like this, it's that promise.all, its type is that it takes an array of promise A and it turns it into a promise of array A. So it's kind of like a transpose operation, or maybe it's also kind of like a distributivity relation. So notice that it switches the position of array and promise and the types. So you used to have a whole bunch of promises in an array, and now you have one promise that contains an array. And so basically what it does is it says, block on all of these things. Wait for all of these things to be ready, and once they're all ready, then you're ready, and then we can just await that. So really what this line is saying, it's saying, wait for the entire program to finish running. And then once the entire program is finished running, then you'll get past this line. And that's when, of course, the program's over. And then the program is over. So that's what we wrote. So this right here is really just telling us what the basic components of both a reach program, it's made up of an application with participants, and then the specification of what the program is. And on the other hand, we have the test apparatus. I'm going to pause now. Any comments or questions before I move on to the next thing?
I'm good over here, Jay.
Great, Chris. So now what we're going to do next is we're going to like actually write a particular program. Now, anytime you're learning anything, you have to learn the technique, and then you have to learn what it's used for. So an analogy that I like to use is think about cooking. So when you cook or bake, let's actually use baking. Yeah. So when you bake, there are techniques that you have to use, like beating and measuring and, putting it in the right spot in the oven. So, I mean, these are the basic techniques, and those techniques you can use no matter what you're baking. On the other hand, you can bake specific dishes like a casserole or cookies or a cake or something like that. And you might not like cookies, but when you make cookies, they have the advantage of being really simple. And the thing is that the techniques that you use when you make cookies are the same techniques that you use when you make something like, glace du beurre, which is just like really delicious dessert. It's like butter ice cream. It's really good. So they're the same techniques, but it's more complicated because you have to apply all of the techniques in very particular orders. And so this is the difference between the domain, that's the cookies, and the techniques, that's the programming language. And so what we're doing in the Reach tutorial is we tried to pick a domain that was the chocolate chip cookies of domains. It's not something super complicated. It's not something that is really weird and foreign. It's a really basic game, the game of rock, paper, scissors. And this is a game that pretty much people already understand, or we can explain really fast. So there are two people play. They simultaneously choose a hand, which is either scissors, rock, or paper. And then they simultaneously choose these. They present them at the same time. And then rock will smash scissors, winning. Scissors will cut paper. And then paper will cover rock. So that's the entire rules of the game. And then we're going to supplement this game with the additional constraint is that there's going to be money on the line. So I'm going to bet somebody $10,000 that I'm going to win in rock, paper, scissors against them. And that is what the tutorial is about. Now, to do that, what we're going to be doing is we're going to be changing the reach program over here. And essentially what we're going to do is we're going to modify the program so it looks like this. It's going to say Alice chooses her hand. And it's going to say Bob chooses his hand. And then it's going to say we figure out who won. Okay. Now, how do we, and then of course, once we choose it, we're going to share the information. So let's kind of start in the middle there. We're going to say Alice is going to share her hand. So she's going to publish hand A. And so even from this first line of code, there's a few interesting ideas. So the first interesting idea is that in reach programs, we refer to sending information, messaging, calling protocol functions, all of those related ideas, we refer to that as publication. And what's publication? Publication is making something available widely for everyone to find out. So when you publish something in the newspaper, you're publishing it so that everyone can see. When you publish a scientific article, you're doing it so that everyone knows what it is. And so the thing that's special about consensus networks is that they don't have directed communication, meaning that Alice does not share something with Bob. Alice shares something with the entire universe, and then everybody can see. So that's why we focus on the fact that Alice is sharing it, not who is she sharing it with, because she's implicitly sharing it with everybody and what she's sharing. So this is going to be another big idea of reach, is that she is going to share program variables. And remember, what a reach program is a DAP. And what's a DAP? It is a decentralized computation. So that means a computation involves values and the operations on those values. So those values have names, the variable names. So she's going to share values. So that, of course, means that she has to already know what that is. So if we look in this program, there's no definition for the hand A variable. So where does it come from? We could write something like hand A equals, and then let's just kind of assume that we're going to use numbers or something like that for rock, paper, scissors, because I like, oh, it's like scissors. So it's just hand A is 2. But this right here isn't really enough information, because what makes this Alice's hand? It doesn't say anything about Alice here. So again, this is kind of the next big idea about reach, is that in reach programs, you can write down that a part of the program is only executed by one party. So we write that like this. So we say that A is the only one that calls this function. This notation right here of the left parenthesis, right parenthesis, arrow, this is called an arrow expression in JavaScript. It is basically an anonymous function, a function that has no name, and here's its body. And so we define the hand A function. So now Alice has defined hand A. Now this is not a very good program if Alice can only ever play hand 2. So what we want to do is we want to make it so that the Alice reach program can interact with the Alice JavaScript program. And the JavaScript program that we're going to write is going to randomly choose hands. But in the future, we're going to write one that's going to interact with the user and ask the user, hey, what hand do you want to play? So we'll go over here and we'll change this. We'll say interact, and we'll say get hand. Now, this is kind of the next big idea about reach. Notice that reach, we've written 3 lines of code, and every single time I write a line, I say, oh, here's a big idea. The reason why we chose the rock, paper, scissors program is because every line is pregnant with big ideas. And there's no extraneous lines. Where the whole program we're going to end up writing is going to be like 50 lines of code, and every line is like really deep with what it tells you about how dApps work. Okay, so the thing that we just wrote is we wrote interact, get hand. So what's going on here? Well, we made a choice when I implemented reach, where I didn't want reach to be the entire program, meaning that I didn't want reach to have to deal with like opening up windows on your screen. And I didn't want to make a version of reach for web browsers and another version for desktop programs, another version for mobile applications. I wanted to define the interface, the level of abstraction that reach works with. And that level of abstraction, I call the front-end, back-end barrier. And that is encapsulated by this object right here. So this object, what it does is it defines all of the functions that the front end, that's this code over here on the right, provides to the back end. And it's going to provide a function that takes no arguments. This is an empty array. And then it returns a number, a uint. So that function getHand is provided by Alice to the reach program. And when the reach program calls it, she acquires the hand A value. Now over here, we can actually write that function. So let's go over here and write it. We could write getHand, and it takes no arguments. And this is what it does. So, there you go. So what are we going to do? Well, let's just like print out a message. So we're going to say Alice chooses the hand, and then she'll pick a hand. And so let's make a little variable. We'll call hands hand, and then we'll return hand, and then now hands be up here. It's going to be rock, paper, and scissors. And then we'll go down here and we'll say that hand is equal to, we're going to pick one of those randomly. How can we randomly do that? We can say math.random, and that picks a number between 0 and 1. We can multiply that by 3, because if you multiply a number between 0 and 1 by 3, 0 and 1 by 3, then that means that you now have a number between 0 and 1. But it's got all sorts of random decimals, so we'll take the floor of that number. We don't want to round because we don't want to go above 3. We don't want to go to 3. We want 0, 1, or 2. And then we'll replace that 3 with hands.length in case we want to change this program to rock, paper, scissors, lizard, Spock later. Okay, so now we'll go up over here and let's just run the program to see how we're doing. So we'll write run in here. So I try to run this program and it's going to error. It's going to say, invalid binding in part only Hende secret identifiers must be prefixed with underscore. Did you mean to declassify? So again, I'm about to tell you, if you're playing the J tutorial drinking game,
another big idea.
Another big idea. Okay, so this big idea is declassify. And what is declassify? Declassify is the button, the window that pops up when you try to close your word processor that says, are you sure you want to close the program? Don't you mean save first? So we basically have an assumption in Reach that every value that starts off known only by one participant via this participant interface is something that is secret that you don't want anyone to ever find out about. And you have to explicitly say that you want to release that information to be allowed to publish it. Now, of course, the fact that you put it inside of the publish also kind of means that you want to share it, but we want to make sure that you double confirm that. And so we have to write declassify. And declassify says this secret information, I'm going to release it to the world. Okay, so now we're ready to go. Okay, we try to run the program again, and it says error. It says invalid operation exit cannot be used in this context. Consensus step must be in step. You must commit first. And notice that it tells you that this error comes on line 20 because we publish the program, we publish Hende, and then we exit because the program's over because we haven't finished writing it yet. And it says you must commit first. And again, this is another big idea. So Reach programs are special compared to programming in JavaScript or Python. Because when you program in JavaScript or Python, you're writing one program that is inside of your, one strand of computation all the time. I see that there's a chat message. I'm going to answer this question. So Nico says, how does Reach know that interact gethand refers to Alice's gethand and not Bob's gethand if he had one? Is it because it is inside a.only? Exactly. It turns out that this interact variable, you actually can't refer to it at all. So even if we tried to write hand equals interact.gethand, this program is just going to error. It's just going to say, what's interact? See, it says invalid unbound identifier in expression interact. This is at line 12, 20. So right there, it says, did you mean interval? It says, here are some things that are bound to this. So interact is just not bound at all. It is not something that you can refer to outside of an only. So since you can only refer to it inside of an only, that means we know whose it belongs to. In this case, it belongs to Alice. Okay. Okay. So when you write Python and JavaScript, your program is running on your computer or on the web browser. It always runs in one mode. But in Reach, programs run in different modes at different parts of the program. For example, we just saw an example of that, how interact can only occur inside of an only. Well, it turns out that publish can only occur in what we call a step. A step is how the program starts off. So the program up here is at a step. Similarly, an exit can only happen at a step. It says must be in step. And then it says, but it's used in a consensus step because after you publish, you now are in what is called a consensus step. A consensus step means this is now the part of the program that's going to check to make sure that Alice followed the rules when she tried to publish this hand. We have a helpful picture inside the documentation. Let me just go over to it. We go to reference and then programs. There's this picture right here of what the different modes are. You call reach app and it is in a step. And then you call publish and you're over here in a consensus step. And when you call commit, you go back to a step. And if you are in a step, then you can call these functions to stay inside of a step. And you can also do an only to go over to a local step, which allows you to do special stuff. And you can come back afterwards. So this program right here we didn't commit. Notice that the error message says, did you mean to commit first? Now we commit. Okay, so now we can run the program. And notice that now it compiled and it's gone off and it started a test development network. And it started up a custom Ethereum server that has its own Ethereum money. And then it says Alice chooses the hand paper. So we ran the program, Alice published that. If we were to go look at the blockchain, we would see, aha, she really published paper. Now, of course, we want to do something very similar to this for Bob. So let's copy and paste this code. This code will change later, so I'm not being completely evil by doing this copy and pasting. I'm only being a little bit evil. Okay, so now let's run it and see what happens. And it says, whoops, you made a mistake. GetHand is not a field of Bob's interaction interface. This is on line 19. So right here, that right there, Bob doesn't have one of those. Because his interact interface is still empty right here. So I think that what we should do is we should pull out this into some common code that we'll call player. So we'll say that a player is anybody that has a getHand function. And now, how do we make it so that we say that Alice and Bob are both players? So there's this principle, which is that programming languages should not be designed by piling feature on top of feature, but by removing the inconsistencies and restrictions that make new features appear necessary. So JavaScript, and thus Reach, already has a way of composing objects together. So we can say that this object right here that specifies what Alice can do, we can say that it just has inside of it everything that's inside of player. And the way that you write that in JavaScript is you write ... and then player. Oops. Let my wrists wait a little bit. Stretch them out. Okay, so we write ... player. So what that means is that this object right here has everything in it that the player object has in it. So that means that Alice has a getHand function and Bob also has a getHand function. Now we can run the program. And it's going to start up our Theorem server. It's going to say, whoops, there's an error. It says, Alice chooses hand, and then it says interact.getHand is not a function at module Bob. So it turns out that we made it so that Alice has a getHand function, but we didn't make it so that Bob has one. So we're actually going to do something extremely similar to what we did over here. We're going to make it so that Alice and Bob both have common functionality. So Bob is going to have the player code, and Alice is also going to have the player code. But now notice that the player code is going to have this getHand function. So let's write the getHand function. So we'll say player equals an object that has this code right here. Right. Okay, now it says Alice chooses the hand paper, and then Alice chooses the hand paper. But I thought Bob was supposed to choose the second one. Well, it turns out that our text string says Alice right there. So we should change this code so it is parameterized over who it is. So we can make an abstraction we'll call who. And we'll say that player isn't just an object. It's actually a function that returns an object. We've now made it so that there's a function that takes one parameter that's who, and it returns an expression. That's what these parentheses do. And that expression is an object. That's what these braces are. And that object has a getHand function that does this code. And now player, Alice will say, oh, this is the Alice player. And over here, this is the Bob player. So we are abstracting over what is common about these. So we'll go run the program again. And we'll see that they both choose scissors. Why do they both choose scissors? Do they always choose the exact same thing? They both choose rock that time. It's really weird. Now they both choose rock again. I'm actually getting kind of freaked out because they shouldn't be. Oh, there we go. Okay, so they don't always do the same thing. Okay. All right. So we're almost done. We said Alice chooses her hand, then Bob chooses his hand. Now we need to figure out who won. Now, figuring out who won should be something that's actually part of the consensus, because this should be a consensual computation. let's skip this for today. We'll say that the outcome. Now, how do we figure out the outcome? We could like make a big table. We could do something like when hand A is equal to raw, and so on. But it turns out that there's a fancy way to do this. What we can do is we can take hand A and we can add to it hand B plus 1, I think. Or maybe it's minus 1. I think it's hand B plus 1. And then we'll modulo this by 3. And when you modulo that by 3, then 0 is going to be Bob wins. And then 1 is going to be Alice wins. And then 2 is going to be a draw. Let me just double check that that's right. I have the function in here somewhere. Okay, it's actually 4 minus hand B. So it's not hand B plus 1. 4 minus hand B. So then, of course, we want to actually see who won. So let's make it so that we have another function up here that's called COutcome. There's a function that takes in a uint and returns nothing. Now, what we want to do is we want to have it so that each person does something. So we could write a.only, and then inside here we could write interact.COutcome, and then we could write outcome so that everyone sees what it was. And then we could copy this code and do it again for Bob. But this is obviously evil. You shouldn't write code like this. So this is a really common thing that happens. So there's a little helper function that's called each. And what each does is it has a list of people, and each one is going to do the same thing. I said people, but I meant participant. Let's go over to our JavaScript code and add to the player interface the COutcome function. And we'll say the outcome, and it's going to be a function. We'll say console.log. We'll say who saw the outcome. We'll say outcomes is outcome. And then we'll return. And let's make another variable over here for outcomes. And it'll say Bob wins, Alice wins, and then a draw. Okay, let's run our code again. And it'll say Alice chooses rock, Bob chooses paper, Alice saw the outcome, Bob wins. Bob saw the outcome, Bob wins. Notice that they both saw the same outcome because the computation was performed consensually. All right, what we've shown here is how to have these things, share, but we've learned a whole lot of techniques that will come in useful later. We've learned the technique that in Reach, you publish things. This is part of the model of Reach, that there are only expressions where a combination is done only by one participant. We have the interact function, or the interact object, which encapsulates the behavior that the front end shares with the back end. We saw how you can specify that right here, and how you can create abstractions by making shared interfaces that are shared by both parties or many parties. We talked about how there are different modes to Reach programs where you have to commit, and as you are in a consensus step, so you can go back to a normal step. And then we saw some clever math to figure out who the winner of a game is. And then we saw in each how to have everyone run the same code. And then over in our JavaScript code, we saw how to construct these interacting objects. Now, there's absolutely nothing special about this getHand function. We don't have to write one that does it randomly. We don't have to have one that has a console log right here. We could have this program like be a web browser. We could have it connect to some sort of like GUI tool code and pop up a window. There's absolutely nothing special about this JavaScript code. It's just normal JavaScript. So anything that your JavaScript program could do, this program could do. So if you have existing JavaScript experience, it will just immediately apply. So that's the next step of the tutorial. How are we doing for questions and thoughts? So we've been going for about an hour, and I originally planned on having BB and Matt do some stuff and have you all, do some programming on your own. Do you feel like this is valuable? You'd like to have more of me going super slowly commentating, or you want to be unleashed and pick up from here? Thanks, Michael. Thanks, BB. Okay, well, I guess we can keep going for a little bit. Let me just confirm something. I'm going to move to a different room. Someone mentioned, I like your commentating. It makes what you copy and paste it. I'm a real believer in muscle memory when it comes to programming. So I would highly encourage you to not copy and paste anything ever in your entire life. Just pry off the C and the V buttons and just don't even have copy and pasting.
What will happen to everybody at Stack Overflow then?
Yeah, I know. See, the thing is that, first of all, it's very valuable to understand exactly what's going on. But also, you learn things by doing them. And so you want to have it just you should be able to close your eyes and just type out, public static void main when you're writing Java programs, for instance. All right, so let's continue a little bit with our example. So what we're going to do is we're going to sort of get ready to have the program deal with money. So that we're going to do that is we're going to extend it so that Alice is going to have the bet that she's going to propose. So we're going to call that the wager, and it's going to be a number. Now notice that previously, all the elements of our interaction interface were functions, but we can actually have them just be values. So we can just say that there's a value here called the wager, and it's a number. And Bob will have his own special function that's going to be called accept wager, and it will take in that number, and it just won't return anything. Okay. And where are we going to put these? Well, we're going to add this one right here. We're going to say that the wager is the declassification of the interact wager. And then we'll publish that value. And then we'll also have Alice pay that value. So notice that we can have interact.wager is just the value, and it's going to be secret, so we have to declassify it. We can publish it, and when we publish it, we can also pay it. Now, just kind of as a little aside, what if we didn't publish it? What if we just tried to pay it? This is actually going to error. So let me show you what the error is and tell you why it errors. Okay, so it says, unbound identifier and expression wager. Did you mean player or these things? This is on line 25. So look right here. What do you mean that's unbound? It's bound right there. Well, the thing is that remember that these values are bound only for Alice. And this computation right here, although it's saying that Alice is going to be the one that publishes this pay component is actually part of the consensus step because it has to be consensually agreed that wager is being published. But we don't know what wager is. And so that means that we have to share wager with everybody so that we can then check to make sure that this value right here really was the wager. And so that's why it has to be published first. Okay. Now we can go over here and try to fill in what this is. So we'll say wager, and let's say it's going to be another parse currency, and let's say that it's going to be 5. So let's see how things go. And it says that there's an error. It says right here that there's a theorem that failed. So one of the things that Reach does is every time you write a program and compile it, it checks to make sure that a large number of general properties are true about what your program does. And one of those properties is that the balance has to be 0 at the application exit. So see, this is on line 41. So if we go to line 41, that's the exit in our program. So we have to make sure that the balance is 0. And when the reach theorem prover checks things, it's going to tell you what is called the theorem formalization. So the theorem formalization says that 0 has to equal, and then it's going to show you the history of everything that came in and out of your program. And so in this case, the thing that went into your program was Alice's interact wager value, because it went in right here. And so this right here, although it's only one value, this is really like an accounting statement. So wager went in and nothing went out. And so we have to prove that that's 0. And then what it's going to do is it's going to show you what's called a violation witness. So this is values. So this theorem formalization may contain variables. And the violation witness is going to tell you, well, those variables could have these values that would make it so that the theorem was false. And so in particular, Alice's wager could be 1, because you just said that Alice gets to pick any number. And so if she picks the number 1, then that means that at the end of the program, it's not going to be 0. And the reason this happens is because wager goes in, but nothing comes out. So let's push along the program a little bit so we can get to where we want. Let's make it so that Bob, what he does is he's going to call interact accept wager, and he's going to get to see it. Now remember how I talked about this whole blocking thing earlier? Well, reach as a programming language, it does blocking. So every time you call interact, that means that your reach program blocks and it waits to have the value. So in this case, Bob, we're going to call the accept wager function and we're going to wait to hear back. So let's go over here and write that function. So accept wager, it takes in a wager value, and let's just have it print out something. It'll say Bob accepts the wager, and then we'll print it out. And we can call the format currency function. What format currency does is it's sort of like the dual of parse currency. And we can say how many decimals we want to show. And then we'll close that. Okay, and if he accepts, meaning that this function's returns, like we could just make it so that, it like calls process exit 0 if the number is too high or something like that. So we can say something like, if wager is greater than, I don't know, this number. Actually, that's really big. I'm not sure we can really do that. We would have to write if wager is greater than or equal to big number of I of a string. Big number. My micro break appeared. And it's not going down for some reason. We'll have it give this honking number. So if it's bigger than that, then we'll quit the program because we don't want to spend that much way. Okay. Okay, so then if he does that, then we'll say that he will pay also the wager. And then we've made a little bit of progress. You run, however, and now it says, oh, you still isn't doing anything because now 0 equals the wager plus the wager because 2 wagers have gone in, but nothing's come out. So now what we'll do is we'll make it so that we'll figure out what will come out. So we'll create a variable called 2a and 2b. And it'll say if the outcome is equal to 0, that's when Bob wins. A will get 0 and Bob will get 2. And then if the outcome is equal to 1, that's when Alice wins. Is it Alice wins or is it draw? Yeah, it's a draw. I read this wrong. Just fix this. Don't be too impressed that I remember this because I wrote it wrong the first time. Okay, so if it's 0, that means that Bob won. If it's 1, that means that it's a draw. And then otherwise, that means that it must be 2. And if it's 2, then that means that we want Alice to win, so she'll get 2 shares. Okay. So then what we'll do is we'll say that we're going to transfer 2A times the wager to A. And we're going to transfer 2B times the wager to B. Okay. So there's a few kind of cool ideas here. These are just sort of like general JavaScript programming things. So the first one is that, you may not have seen the ternary operator before. It's a way of writing an if statement in the expression position. So we're going to say, if this condition is true, return this. Otherwise, do this code. And if this condition is true, return this. Otherwise, do this code. Now, the next thing is that notice that we have an array right here on the right-hand side, and we also have an array over here on the left-hand side. So what this does is it's going to make it so that 2A is bound either to 0, 1, or 2, and 2B is bound either to 2, 1, or 0. So this is called a destructuring assignment, and it is something that JavaScript and Reach supports. The next thing is that one of the things that we do in Reach programs is that we manage money. And so we are going to be able to transfer some funds to A or transfer some funds to Bob to B. And I've written it this way with the destructuring and the multiplication and whatnot, just so that it, the program can be short, because I'm obsessed with making short programs. I'm obsessed with making good programs, but good and short is even better than good. Okay, so now let's run the program and we'll see what happens. So it compiled and now it ran. And it'll say that Alice uses paper, Bob accepts the wager 5, and then it just says over. It must be, it must be that this actually is too small because this number right here, even though I thought it was big, I don't think it has 18 digits. So since it doesn't have 18 digits, it actually is, Bob does quit. So let's get rid of that. Remember, on Ethereum, like the number 5 would be really 5 times 10 to the 18. So it's like really big. Okay, there we go. Now, although we saw that Alice won, we don't really like see that, like what money changed hands. So let's add some extra printouts. We'll say console.log, and we'll say Alice went from her before currency. We'll say before to after. And we'll say before A and after A. And then we'll say Bob went from before B to after B. And actually, let's call this function format, which we'll write format and format. Format and format. If I were cool, I would learn how to make multiple cursors. Okay, so we'll say that after A is going to be equal to the balance of, I think that's what it's called. Let me look. Get balance. Say await get balance of Alice. And then we'll say after B is get balance of Bob. This is actually the account of these guys. And then we'll do the same thing up here for their before. So we'll say before and before. Now we'll define these functions. So format is going to be equal to calling standard lib format currency of X and 4. And we actually kind of use that over here when we printed out the wager. So let's actually use that. We'll say format the wager. And then we'll write this get balance function. Get balance is, I think that it's just standard lib First of all, asynchronous. I think it's await standard lib balance of x. I think that's right. Yeah. There we go. Okay. So let's run and see if it works. And it looks good. Okay, so this JavaScript program doesn't really have anything too new. You know, we're defining a helper function, we're defining another helper function. We're exploring what is available in the standard library, this balance of function. You know, you are following the tutorial, but you may ask yourself, like, how would I know about that balance of function? How would I know that I could do that? Let's just pop over to the documentation for just a moment. So the program section tells you about writing reach programs, but the front-end support tells you about writing front-ends, and there's ways to do it in JavaScript and Python and Go, but let's look at the JavaScript one. That's kind of the main one. If we go under accounts, here are things that you can do to accounts. You can get the default account. You can create new ones. One of the things you can do is you can call balance of. It says returns a promise for the balance of network tokens held by the account given by a reach account abstraction provided by the account argument. Is there something in the consensus check to make sure the money being transferred doesn't exceed the money in the wagers? Yeah. So let me go do that in a moment. So yeah, so we have just basically just added a little bit of more user interface, but there's nothing really exciting here. Now, so the question was like, what if we saw it checking to make sure that we spent everything, but what if we tried to like spend too much? Like, let's make it so that if there's a draw, that we try to give 1 share to Alice and 2 shares to Bob. This is bad. So something that's going to be cool about this, actually, let me do it so that it's only when Bob wins. If Bob wins, then he gets 3 times the amount. So when we run this, it's going to say that a theorem failed. It's going to say that the theorem was the balance sufficient for transfer, and this is on line 42, which is right there, see 42. And it says that the theorem formalization is that V48 times 1, sorry, V48 times Alice's wager has to be less than Alice's wager plus Alice's wager minus V48 times Alice's wager. And what is V48? Well, V48 is this computation right here, which would be 0 and 3. And it would be 0, 3 because outcome would be 0. Outcome is this value. And if it's 0, then that means it's 0, 3. Now, why would it be 0? Why would the outcome be 0? Well, because A could have played the hand 0, and B could have played the hand 4. What would 4 be, by the way? 0 is rock, right? And then we have paper and then scissors. And then we have, so there's rock, paper, scissors, rock, paper. So it's paper. So paper beats rock. Yeah, so not only has it figured out that this theorem is false, it's figured out that that's because the outcome would be the certain way, and the outcome would only be that certain way if people played these particular hands. So when it is verifying your program, it considers anything that could potentially happen and all the bad things that could go along with that thing potentially happening. Okay, so we've now made it so that our program actually deals with money. It is cool. So it turns out, though, that our program is really bad. And our program is really bad because it's not actually secure. And the reason it's not secure is because Alice shares her hand first. And because she shares her hand first, it's actually possible for Bob to just always win. And here we'll change it so that Bob always wins. So I'm going to comment out this code right here, and I'm going to replace it with hand B equals hand A plus 1. That's going to make it so that Bob always wins. because rock is always beaten by paper. Paper is always beaten by scissors. Scissors is always beaten by rock. Oh, and I gotta fix this right here. Every time I run this program, Bob is gonna win. See, Alice chooses rock. Bob, we didn't even run his function because we did it automatically. We'll do it again. Bob won again when she played scissors. And now we'll do it one more time. And paper. Okay. So the problem is that Alice shares her hand openly. And because she does that, that means that Bob doesn't have to actually run this program right here. And there's actually no way to enforce that Bob runs the program that we want. All we know is that Bob is responsible for sharing some number, and he can get that number any way that he wants. This is actually why when you look at the verification, it says that we verify the program. Let me go back to where it was compiled. It says verifying when all participants are honest. Sorry. It says verifying when all participants are honest, when no participants are honest, when only Alice is honest, and when only Bob is honest. What it means by honest is, let's assume that they really run their only functions. And then we're going to assume that they don't run any only functions. And then we're going to assume that only Alice runs her only functions. Everybody else just does whatever they feel like. And so what this is going to do is it's going to check to see if there is enough constraints in the consensus to guarantee good behavior. And it checks all the same theorems. Okay, so how do we deal with this? Basically what we need to do is we need to learn a cryptographic technique. Remember I talked about how we're doing rock, paper, scissors so we can learn a whole bunch of techniques in a boring domain. So we're learning JavaScript techniques, we're learning reach techniques, we're learning programming techniques. Now we're going to learn a cryptography technique. And this cryptography technique is called commitment. And the way that the commitment pattern works is rather than sharing our actual hand, what we're going to do is we're going to share a basically a encrypted version of it. It turns out that it's not actually an encrypted version. Encryption isn't the right word. It's more like a signature. And actually, signature isn't quite the right word either, because a signature means that you can tell who signed it. This is actually an even more basic thing. It's called a digest. So what we're going to do is we're going to call the function. Let's call it hand A underscore. Then we're going to say that there's going to be a salt A and a commitment A. And we'll call make commitment interact hand A. Let's just make sure I got those arguments right. Well, you know what? I forgot that I want to actually do something else first. Do hand A equals classify hand A. So before I actually show you the fix, one of the things I want to mention is that every time you find an error in your program, your goal should be to get reach to find that error. And the only way that reach can find errors in your program is if you add more assertions. Now, behind the scenes, there are assertions about transfer amounts being, big enough, things like that. But there's another kind of assertion that reach can reason about, which is called knowledge. So we can write a knowledge theorem. So we can say unknowable. It is unknowable for Bob to find out what A knows about the variable hand A. So we can write that theorem right there. It says, Bob doesn't know what A knows about hand A. Now, when we try to run this program, it's going to fail because I wrote unknowable. What I meant to write, unknowable. Now when we run it, it's going to fail for a different reason. It's going to fail because Bob knows of hand A because it is published. So it will say, right here on line 31, see 31, you wanted to make sure that Bob didn't know this, but actually he knows it because it was published right there. Okay, well, let's just make it so it doesn't get published. So now it's not published, but we need to publish something else. So we publish what's called the commitment. Let me just make sure I got these arguments in the right order, the results in the right order. And the arguments come up. The commitment is first. That's what I was looking for. Commitment, and then the salt. Okay. So instead, we're going to publish the commitment. We'll say commit A equals to classify commit A. So now we'll run the program. And we're going to get a different error. And the different error is going to say that you can't call make commitment. It says random is not a field of Alice's interaction interface. So make commitment assumes that the participant provides random numbers. The way that we can do that is we can say that Alice has to have randomness. So we say has random, just like we say that Alice has the player interface. We'll say that it has random. We can get random by doing over here, standard lib dot has random. So now we've solved that problem. We'll get a new problem. Now it says unbound identifier right there. So on line 32, we are trying to refer to hand A, but hand A actually isn't even a variable in the program. So we'll change it to underscore hand A. Okay, now on line 40, hand A isn't a variable. And that's because, well, we're not showing it anymore. So because we're not showing it, we'll have to come back and have Alice do another publish. So we'll have her come back and we'll say that hand A is equal to the declassification of hand A. Actually, we'll have her declassify the hand and the salt. Salt A. Actually, you know what? I'm giving something away. So let's have her only declassify the hand. And then we'll say that she will publish hand A, and then now it is available. Notice that these knowledge claims are like time sensitive. Bob doesn't know what hand A is right now, but he does know what it is later. Okay, so now we run the program, and it says Alice chooses paper, Bob chooses rock, and Alice wins. Now, it appears that there's no way for Bob to know what hand A is. Therefore, he has to really call this function. He can't do something else. Now, I mentioned just a moment ago that that there's a slight mistake in this program. And this mistake is that we can actually make it so that Alice always wins. So see right here where it says Alice chose scissors and then Bob chose rock. Well, we can actually make it so that Alice doesn't publish what her real hand is. Instead, we could make it so she publishes whatever would make her win. So we could say that hand A is equal to hand B plus 1. Now, this is going to make it so that Bob will never win, and it'll never draw. Every time we run this, it'll always say Alice wins, because Alice is cheating. This is that's a real win. Let's wait until there's one where she lies. Okay, so this is a good example. So see, Alice chose scissors and committed to scissors, and then Bob chose rock, but Alice still won. And the reason she won is because she didn't actually submit the thing that she chose before. She decided what she was going to do based on what Bob did. Now we can't do the same strategy anymore because somebody has to reveal it first. So it's not that Alice doesn't know what hand B is, it's that she doesn't have a choice about what to publish. So what we're going to do is we're going to write check commitment. So we're going to check to make sure, and I always forget the order of these arguments. It goes the commit and then the salt. So commit A, salt A, hand A. So we have to check to see that this commitment that she published earlier matches what she just published. Now, of course, she hasn't published all of those things because she didn't publish the salt. So it says salt isn't defined. So we'll say, okay, so she's going to publish the salt. So we'll go over here and we'll say salt A equals declassify of salt A. Now we're still trying to lie, by the way. And it says, okay, well, if I try to verify this when all the participants are honest, then this check commit right here doesn't work. And because it doesn't work, that means that because this digest right here doesn't match that because it's supposed to match X, but it actually is hand B plus 1. So what this means is that if Alice is being honest, she won't be able to actually run her code, and she'll never be able to send this message. But we're actually not. There's no violation when Alice, when nobody's dishonest. And that's because we are correctly checking everything. So what we need to do is we need to get rid of the lie and replace it with the truth. Okay, so pass the theorem prover. And now it's going to actually be fair. Every time we run, it's going to work. And Bob can win and Alice can win. Now, we're getting close to the end of when I want to be doing this. So I want to show you kind of a few behind the scenes things. So we've been testing this whole time on Theorem, but it will actually work if we do it on Algorand. So let me write reach connector mode equals algo. Remember I told you that when we load the standard library right here, it looks at our environment to determine what we want to do. That's what I mean. It's looking at this variable right here to see what network you want to use. And we're going to use Algorand. Algorand is going to take a little bit longer in test scenarios. And that's because it runs at like the network speed, which is much faster than Ethereum, but it's slower than the test network. Now, the other thing that I want to show you while we're waiting for that to go is we can go look at the actual compiled code as a comment. Should we change the currency amount when moving to Algorand? No. That's why we abstracted everything with the parse currency and format currency. We're still using 10 units. It's just that those 10 units, they used to be ETH and then now they're algo, but everything will just work out fine. That's actually why, format currency, parse currency, that's why they exist. So it makes it easier to write a blockchain agnostic program. And there's an error. Oh. Okay. So my standard library is out of date. Sometimes you'll get errors like this when your code, when I update the compiler, but you have like an old version of things, you'll get kind of a weird error. And so you can just run reach update and it will download new images. You might wonder, why don't I have accurate images? Well, the reason I don't have the correct images is because I only ever run the development version, and the development version just completely ignores all this Docker stuff and uses ones that are like part of my development system. So that's why I don't have the new ones. Well, it's not that I don't. It's not that I. Yeah, it's like basically I have the new ones. It's just that they're like labeled wrong. They're like labeled with these development tags. Now I have to get the actual released ones to be able to run this program right. All right. That's the one that really matters, that runner thing. That runner is the actual like test harness. All right, there we go. Okay, now let's run again. Okay. So while that's running, we're going to look at the compiled version, the compiled code. And this sort of just, this is just curiosity that I'm showing you. So remember in our, what happened now? Error again. Did I not? Okay, so let's do Docker clean. This is going to like delete all my Docker images. Remove that. And then we will remove the build. File. And we'll run. Okay. Okay, so remember that we called this backend.alice function. Well, that's this function right here. Let me open it up so you can see what I'm talking about. So in our code, we ran backend.alice and we gave it the contract and we gave it the interact object. Well, we can see that's this function right here. It got the contract and it got the interact object. And inside of this, you can sort of see the compiled form of all the stuff that we did. So for instance, there's this call to getHand right here. Well, that's this right here. So we call getHand, and then we get a random number. That random number, we can see, oh, this is being called inside of make commitment. That was being called inside of this other thing. And then we call digest, because that's really what the commitment is. It's a digest of the random number and our hand. And then that V26, that's what we're going to publish. And we can see that it gets published because it got published right here. We published V26, which is the commitment, and we also published 18, which is the wager. If we look back, we'll see that 18 equals wager, see? So anyways, so this is kind of a curiosity. You can kind of see what's going on and notice that it's only, one half of things. There's that send up here for the first publish, and then there's a receive down here for when we receive Bob's hand, which is V39. And if we look deeper in, we can see, Bob's code. And then we can also see down here the code that implemented on Algorand. And did it actually run? What's going on? It didn't print out anything. Why didn't it print out anything? I feel like I'm going insane. That's really weird.
Your micro break is on.
Yeah, my micro break is on. That shouldn't be why. Did I accidentally kill it? I don't know. Okay, well, let's ignore that for now. But anyways, oh yeah, this is what I wanted to show you. When we compile, we can give it an extra option, which is called intermediate files. And when you compile with intermediate files, you'll get not only this file that shows you the Algorand source code, you'll also get another one. For some reason, every time when I am screen sharing and I do this example, and I use intermediate files, it seems like it hangs forever. But then when I do it a second time, it doesn't seem to. I don't understand what's going on. So it's making this file. I wonder if it's because of permissions or something. I don't know. It's really weird. This is really weird. So you can see what your Docker images are doing by looking at your Docker dashboard. And see, this right here is the reach code. It has no output, so it hasn't printed out anything. But see, there's this insane CPU usage for some reason. It's using all this memory. I feel like this is must be some weird artifact of it's got that. Oh, there we go. What did I do? I didn't do anything. All right. So anyway, so when we did that, I created all of these intermediate files that tell us about how the compilation worked. And pretty much all of them are, not really interesting to you, but one of them may be if you've ever used Solidity before, because you can see the Solidity program that we generate. And just like looking at the JavaScript output, sometimes looking at the Solidity, I don't know, can satisfy your curiosity about how things work. So you can see the constructor corresponds to, what happens before the first publish. And then the first message, which is called M1, it contains in it this commitment and this wager. And so we can see that what the program does is it checks to make sure that the value that came along matches the argument v30, which is that wager value. And then we save for later who the sender was, because we need to make sure that later on it's the exact same person down here in message 3. We also check, we also remember what the commitment was and what the wager was. And we save these for later. So if we go down to message 3, actually message 2 is good. So message 2, see, we're going to check to make sure that the value is the same as what we saved before, variable 30. And then if we look at message 3, notice that what it does is it checks to make sure that no money came along with it. It came from Alice. And we check to make sure that if we take variables 47 and 48, which are this published thing, the salt in the hand, and we digest those together, then that equals 29, which is the commitment that we saved before. Then if those things are true, then what we can do is we can compute who the winner is, and then transfer the funds appropriately. So if you're a Solidity expert, then you can see what's going on. And if you're not a Solidity expert, then you can look at this code and say, I'm glad I didn't write that. And similarly, you can see the same thing for the Teal program. Teal is what the virtual machine for Algorand is called. So this right here is the exact same logic, but written in this stack-based language for Teal. So if we look at a little component, we can see something like yeah, like right here. This is us checking to make sure that the commitment matches. So variable 254 is the commitment, and then these values right here are the salt in the hand, which we concatenate them together and then digest them, and then we make sure that that's equal to 254. 254 came in right here. It was part of the arguments to the function. So anyways, so I've given you the play-by-play for sections 1 through 5. What you really want to do is I highly recommend you going through the rest of the tutorial yourself and go slow, read it out loud, copy every word by every letter by hand, and when you read it out loud, imitate my voice as much as you can, and you'll get something almost as good as this tutorial experience that you've just had. So, any final questions before saying goodbye for the night? Oh, cool.
Thank you so much.
So, and when you're done with the tutorial, what you should do is join our Discord, follow along in our community to get more involved as we do, our next bounty hack. And the documentation, has all sorts of exhaustive resources on the language and the support libraries and stuff like that. And then we also have a bunch of project ideas that you can do in the workshop section. And yeah, so let's get hacking.
And we're also going to be sharing the video and upload it on YouTube. I think this was great, Jay. Thanks a lot. It's actually something you can rewatch and, check and double check. And it was definitely a thorough guide. So thanks for that. And thanks for staying on until the end, I guess. And yeah, we lost some people in the way, but definitely we're gonna follow up with them. I saw someone said like, "Oh yeah, I'm just gonna go and try it myself at this point." Cool. I guess that's it. Thanks a lot again. And yeah, we'll keep in touch. And UCSB is definitely a great community for developers. So probably when we go back in person, it might be nice to have you guys. First of all, visit California and UCSB as a campus, which is amazing. But and also in-person hackathons are a lot of fun. So hopefully we can set up something. I want to thank Patrick as well. And Garam left. Yes, he had to go. But thanks for setting this up and helping us. Thanks, Alexis. And also the Reach team for with us and helping on the way.
Yeah, thank you so much for everything. I actually had a couple of questions about Reach itself. When you guys currently support Algorand and Ethereum, what is that? Do you have to work in collaboration with those foundations and have their permissions to use their resources, or how do you guys have to work together to merge some sort of code base together?
No. So from the perspective of Ethereum and Algorand, we're just programs. So anybody could write Ethereum programs. Anybody could write Algorand programs. As it happens, we do have quite a good relationship with Algorand. We received a grant from the Algorand Foundation, and we've become quite close partners with Algorand. Early on, we received a grant from an Ethereum adjacent foundation as well to help us do development. But that's really that's really their foundations supporting their community, as opposed to giving us any sort of internal knowledge or access that that anyone else wouldn't have. Anyone could have written Reach by just reading the Algorand documentation and writing it themselves. And I would not say that our Algorand implementation relies on, I don't know, me having special conversations with anybody at Algorand. I have made some patches to Algorand to add features that I found useful, but again, those could have been added by anybody. They have, open source tools and whatnot. We haven't needed to do something like that on Ethereum because it's way more established. And so it didn't, there wasn't any holes that needed to be filled.
Okay, for sure. I also had a question on like the day-to-day responsibilities of a typical like developer at Reach. Is it a lot of like compiler work, a lot of documentation writing? Like, I don't know.
Yeah, I mean, I can answer this, but this is just so you know, this is like a very specific question to like Reach. I'm not really sure it's like super applicable to anybody, but at Reach we have developer relations engineers who are like Matt and BB on this call, who work with developers to help support them, and they work on documentation and tutorials and things like that. And then we also have people working on the runtime system, which is like, that JavaScript library that I showed you. The sort of the DevOps side of working on, like the test networks, things like that. And then there's the compiler itself. And then things, adjacent to that. And so, yeah, like basically, all of those somebody has to do.
Yeah.
And definitely a big part of it is the compiler. But I would say that like if you think Reach is just a compiler, then you don't know Reach. You know what I mean? There's a lot more going on. The compiler is cool, but you like to have something that is useful to lots of people, it needs to be more than just a cool compiler.
Yeah, for sure.
And if you're curious, the compiler is written in Haskell, and then we use the Z3 theorem prover internally.
Okay. Yeah.
Z3 is a very standard theorem prover that implements the SMT interface, which is like SMT is like a category of theory. It's called an equational theory. So it's like a category of kinds of equations. So saying SMT is like saying linear optimization or SQL or something like that. It's like a subdomain of things that can be proved. Any other questions, Patrick? Or anyone else?
I have one more about
Sure.
job opportunities at Reach and internship opportunities. Do you guys usually like look for out of undergrad students, or are you guys looking for like more well-seasoned developers?
We take anybody. I don't think that we're interested in talent and drive, not credentials. So, we have people who have, been in the industry for a long time, and we have people who, wear their second job after undergrad.
Okay.
So I think that what Chris mentioned before about being part of the community, doing the bounty hacks, those are great ways to practice your Reach programming, get into this kind of world. And, as far as directly working for Reach, we'll be definitely posting job ads, stuff like that. And we'll probably post those on our Discord community in addition to other venues.
For sure. Yeah. Thank you.
Cool.
Amazing. All right. Yeah, we're almost 9 here on the West Coast. This is way later. So Jay, thanks again. Go enjoy your family. We have plenty of follow-up here, Discord. if you guys have any announcement that you want us to blast out, like through emails or whatever, just let us know. And other than that, this was amazing. Thanks a lot again.
Okay, thanks, PG.